Hello, let us start today's lecture from logic gates. The basic definition of a logic gate is, the logic gates are the basic building block of any digital system. It is an electronic circuit having one or more than one input and only one output. The relationship between the input and the output is based on certain logic. Based on these logic gates are named as AND gate, OR gate, NOT gate, etc. Let us first of all see the AND gate. Now this AND gate, it performs an AND operation. The AND operation is nothing but it's a multiplication of the two inputs, or you can say it has n inputs and one output, and the logic is that y is equal to a and of b and of c, and if it's having number n inputs, then it can be said that a dot b dot c dot d dot and so on till n, or it can be also written as a b c n till n. The logic symbol or logic diagram for the AND gate is given by this symbol that's shown in the figure. We have two inputs A and B and one output Y, and there is a symbol like D which represents the AND gate. Now we can define the AND gate using a truth table by taking logic 0 and logic 1. If the input of two input AND gate having input A and B, if we take both of them as a logic 0, so 0 dot 0 will be 0, output will be 0. Similarly, if A is 0 and B is 1, now as per the AND logic it should be dotted, so 0 dot 1 will be 0. Similarly, if A is 1 and B is 0, so 1 dot 0 will be again 0. It will be only 1 when both the input will be 1 or high. If A and B both are 1, then you will get it logic 1. Now the second gate. The second gate is OR gate. A circuit which performs an OR operation is shown in figure. It has n inputs and one output, and this n is always greater than 2. Now this the logic expression for this will be y equals to a or b or c till n, or it can be written as a Boolean expression as y is equal to a plus b plus c plus so on till n. The logic diagram or logic symbol for OR gate will be something like this, which is this is a two input OR gate which is having a output y and input a and b. Now for this we can write a truth table something like this. When input a is 0, and input b is 0, so 0 plus 0 is 0. Again, second part in which a is 0, b is 1, the output will be 0 plus 1, which is 1. And the third input of the table is a is 1, b is 0, the output will be a plus b equals to 1. And last, 1 plus 1 is equal to 1, 0, so we will take the output as 1. So this is the truth table for the two input OR gate. The next gate is NOT gate, which is also known as inverter. Okay, so this simply inverts the input value. If the input is high, you will be getting output as low. If input is low, you will be getting output as high. Or you can say that if you are putting 1 input, you are getting output as 0. If you are putting input as 0, you will be getting output as 1. Or it is simply y equals to a bar. The logic diagram for this is in the triangular shape with a bubble at the output. This is a single input NOT gate. The truth table will be simple. A is 0, you will be getting output B1. If A is 1, output B is 0. These three gates, AND, OR, NOT, these are known as basic logic gates. Okay, next we are moving toward universal gates. And universal gate, we first of all see the NAND gate. NAND gate is a simply combination of AND operation with NOT operation. As we have seen that in the AND operation, we just simply do the dot product of the two inputs. In this multiplication is inverted by simply applying the NOT gate in front of AND gate. That's why it's a NOT AND operation and known as NAND operation. It has n inputs, okay, and this n can be greater than or equal to 2 and one output which can be logically written as y is equal to a not AND of b, not AND of c up till n, or you can write it as a NAND b NAND c and so on, or it can be simply for the two input it can be simply represented as y equals to ab bar. Now, the logic diagram for the NAND gate will be simply just as I explained in the previous slide, that it's a inverter of the AND part. Okay, so therefore I am applying the inverter to the AND output, and this can be shown as inverted AND gate by using a bubble in the front of AND symbol. The NAND symbol will be simply the bubble AND symbol as shown in figure. Now, this NAND gate can again be explained by the truth table. As I already said that it is the inverted AND. So for the AND operation, we usually dot product the inputs for the first input in the table, that is which is having a equals to 0 and b equals to 0. 0 dot 0 is 0 and it is inverted of AND, therefore the final output will be 1. If again I say that if a is 0 and b is 1, the dot product of this will be 0 and the inverted of the dot product will be 1. For if a is 1 and b is 0, again the AND output will be 0, and if it is inverted, you will be getting 1. When both the inputs are 1, the output will be 1 for AND, and if it is inverted, you will be getting 0. So this is how the NAND gate is being explained using this table. The second universal gate is NOR gate. NOR gate is simply again inverted OR operation. In this we invert the OR operation, therefore it is known as NOR operation. It has again an input which can be greater than or equal to 2 and one output. It can be resembled as A not OR of B, not OR of C, not OR again till n, or it can be written as A nor B nor C up till n, or for the two input we can simply say that y is equal to A plus B whole bar. Now the logic gate for this, logic symbol of this, as I explained in the previous slide, that it is the inverted OR. So I have applied an inverter to the output of the OR gate, and both together can be shown in the second, as shown in second diagram. Though both can be assembled as inverter or as a bubbled OR gate, which is nothing but a NOR gate. symbol. Again, this can be explained by its truth table. If for the two input NOR gate, when A and B both are 0, we for an for an OR operation you get 0 plus 0 equals to 0. If it is inverted, you will be getting 1. 0 plus 1 is again 1. 1 is inverted, and you will be getting 0. 1 plus 0 is again 1, which is inverted, you will be getting 0. And finally, if both the inputs are 1, you will be getting 1 plus 1 equals to 1. And if it is inverted, you will be getting 0. So this is how the NOR gate operated. These both gates are known as universal gate because from these gates we can form all the basic gates by using NAND and NOR, which will be explained in the next lecture. That's why these two gates are known as universal gates. One other important gate is XOR gate. XOR gate is a special type of gate. It can be used in the half adder, full adder, other subtractor sector. The exclusive OR is abbreviated as XOR. This is again an input gate. It can be, that means it can be equal to 2 or greater than 2 inputs and 1 output. It is resembled as A XOR B, XOR C, till N. The symbol of XOR is given by plus over in a circle over that, and or you can say it is an encircled plus. For a 2-input XOR gate, the logic expression is Y is equal to AB bar plus A bar B. The logic expression for the XOR gate is shown in this figure. It almost resembles to OR gate with the exception that it has some curve at the end again, 2 curves at the end. Now, XOR gate can be explained by this truth table, in which it can be seen that if both the inputs are having same value, the output is 0. If both the inputs are not similar, then the output is 1. Both are similar, that means if it is 0, 0, you will be getting 0. If both are 1, 1, again you will be getting 0. If it is not similar, then you will be getting 1. For the second and third line, that is if A is 0 and B is 1, you will be getting 1. And if A is 1 and B is 0, the output will be 1. Which shows that it is exclusive OR. Exclusively ORing the inputs. If the inputs are not similar, you will be getting output as high. And the last gate, that is XNOR gate, it is again a special gate which can be used in half adder, full adder, which we'll be studying in the next unit. The exclusive NOR gate is abbreviated as XNOR gate and sometimes as XNOR gate. It has n inputs, and this n can be equal to 2 or it can be greater than 2. The symbol of logical symbol of the XNOR is encircled minus sign, which is shown in the expression below. So we can write a logical expression as Y equals to XOR, it's XNOR B, XNOR C until N, or encircle negative sign. For 2-input logic, 2-input gate, the logic expression can be written as Y equals to A bar B bar plus A B. According to this expression, we can now give the XNOR gate signal. Sorry. The XNOR gate symbol is something is similar to XOR but with a bubble sign at the output. Now, yes, now the truth table of the XNOR gate can be, it's just opposite of the XOR gate. In this case, when all the inputs are same, then the output will be high. As we can say in the first case, 0, 0, we are getting output as 1. And in the last case also, when both the inputs are same, 1, 1, we are getting output as 1. Now, for indifferent output, we are getting logic 0. When A is 0, B is 1, when it is 0. And if it is A is 1 and B is 0, the output is 0. So, or we can say simply that it's inverter of XOR output. With this, we finish all the gates. Okay. Okay. As I told that NAND and NOR gate are universal gate. As it can be used to make another logic gates. Okay, let us see. Now I'm implementing AND gate using universal gate. Now, if you are by using NAND gate, the AND gate can be implemented by using two NAND gate, as shown in figure. I have just put a NAND gate in the front of another NAND gate by simply supplying the output of the first NAND gate to both the inputs of the second NAND gate. If we see now, for example, if we verify by the truth table, so when X and Y both are 0, we will be getting the NAND output as 1, and this, if both the input of NAND gate are 1, we will get output, final output will be 0. In the similar way, we can verify the entire truth table using these two AND gates. Now, let us implement this AND gate using NOR gate. Okay, now to implement this, we require 3 NOR gates. As we can see that there are 2 NOR gates which are whose inputs are shorted and given one input X and another as an input Y, and the output of this two both XOR gate is again fed to the third NOR gate. Now, if you see the apply the inputs, now if I apply 0 to this, 0 and 0 to this NOR gate will give you an output 1. Similarly for Y, if both the inputs are 0, you will be getting 1. Okay, now 1 plus 1 V was 1 and inverter was 0, so final output will be 0. Now let us see the second part, second row. If X is 1, the output is 0 of this first XOR gate. If Y is 0, the output will be 1 for this second XOR gate. If this is 0, this output is 0, and this output is 1, the output will be, output of the third gate will be, XOR gate will, NOR gate will be 0. Now let us see the third row. Now X is 1 and Y is 1. If X is 1, both the input is 1, you will be getting 0 over here. Both the input is 1 over here, you will be getting 0 again. This 0 0 to this XOR gate will give you 1 output. And similarly for the last part, if this is 0, if these two inputs are 0, you will be getting 1 here. If these two inputs are 1, you will be getting 0 here. If this is 1, this is 0, you will be getting 0. In this way, we can verify the truth table of the AND. And this, if you remember that, this is the truth table of an AND gate. 0.0 is equal to 0, 1.0 is equal to 0, 1.1 is 1, 0.1 is 0. Now, let us implement OR gate using universal gate. Now, OR gate using NAND gate. If you are using NAND gate and you have to make it, you have to implement for OR gate, you require 3 NAND gates. Now they can be configured as shown in figure. Now let us verify the truth table. Here, if X is 0 and Y is 0, so if these two inputs are 0, the first NAND gate output will be 1. Similarly, the second NAND gate output will be 1. If these two 1 and 1, the final output will be 0. Now let us see the second row. When X is 0, the first NAND gate's output will be 1. This second NAND gate output for one input will be 0. 1 and 0, you will be getting 1 output. Similarly, for X as 1, Y is 0, this X input 1, then you will be getting 0 output from the first NAND gate and 1 output from the second NAND gate. This will yield you the final output as 1. If both are 1, X and Y both are 1, then the output of the first NAND gate is 0. Output of the second NAND gate is also 0. If both these 0 are given to the third NAND gate, the final output is 1. Now let us implement this OR gate by NOR gate. It is wrongly written over here. It's NOR gate, not NAND gate. NOR gate. So NOR gate, if you are, then simply I am implementing X and Y. I am getting an output of a NOR, which is given to the second NOR. It will be used as an inverter, and you will be getting the inverted output of a NOR. The inverted output of the NOR is nothing but the OR. Okay. Now NOT gate. NOT gate, using NOT gate is simply short both the inputs and give the 0. You will be getting 1 as the output. If you are giving 1, you will be getting 0 as the output. As we know that for the NOR gate case, if both the inputs are 0, output is 1, and both the inputs are 1, output is 0 for the NOR gate case. Now using NAND gate, in the NAND gate also the same thing. If we short both the inputs, we can use it as an inverter. As we know that if 0 0 is given to a NAND gate, the output is 1. When 1 1 is given to the NAND gate, output is 0. So in this way, we can implement NOT gate using the universal gate. So as we see that in this, that all the gates can be formed using the universal gates, using the NAND and NOR gate. You can also implement further other gates, for example, XOR, XNOR, or you can implement any Boolean expression using the NAND gates and NOR gate. That's why these gates are known as universal gates. Okay, so we will be using this universal gate in the next lecture, where we will be implementing all other Boolean expressions, these universal gates. Now let us summarize the what we have learned in this lecture, what we have seen in this lecture. I just summarized these logic gates. The first basic logic gate was AND, whose symbol was given by this, and the algebraic function was x dot of y. This truth table is given by 0, 0 equals to 0, 0, 1 equals to 0, 1, 0 equals to 0, 1, 1 equals to 1. The second basic logic gate was OR gate, symbol given by this, and the algebraic function is f is equal to x plus y. The truth table for this is 0, 0, 0, 0, 1 equals to 1, 1, 0 equals to 1, 1, 1 equals to 1. Third basic logic gate was inverter, which simply inverts the what you give it to the input. It's simply the complement of the input. If you put 0, you will get output as 1. If you put input as 1, you will get output as 0. And then we have seen the universal gate NAND and NOR. NAND is simple a bubbled AND gate, which is given by f is equal to xy bar. You can write it bar, or you can also write as complement. For this, the truth table will be 0, 0 equals to 1, 0, 1 equals to 1, 1, 0 equals to 1, 1, 1 equals to 0. You can easily see this with the previous one. That this is the complement of this truth table. If you go through, this is 0, 0, 0, 0, 1, and this is 1, 1, 1, 0. It's simply the complement of the AND gate truth table. Similarly, if you go through NOR truth table, it is simply a bubbled OR, which Boolean expression is given as f is equal to x plus y bar, or it can be written as complement like this. And here the truth table is 0, 0, which gives you an output 1, 0, 1 will be giving you 0, 1, 0, 0, 1, 1, 0. Again, you can find that this is the complement of the OR truth table. If you go to the OR truth table, it is 0, 1, 1, 1. The NOR will be simply, it will be 1, 0, 0, 0. See, it's 1, 0, 0, 0. Next special logic gate that we have seen, that was exclusive OR, which is given by a line at the end of our gate, which is given by x circle plus y, or xy bar plus x bar y. Here, when both the inputs are same, you get a 0. If both the inputs are not same, then you get a response 1. Exclusive NOR is simply the inverted form of XOR. Okay, therefore it is, the bubble is encircled over here in the front of XOR, and its expression is xy plus x bar y bar, or x complement y complement, and again this is x plus y bar complement encircled, or it can be written as x encircled minus y. Now you can see both the truth table, it's simply the complement of each other. In the XNOR case, when both the input are same, we get the answer 1, and when the input are not same, then we get answer 0. It's just simply opposite data of what is in the XOR. With this, we come to the end of this lecture on logic gates. Hope you have enjoyed. We will be implementing this logic gates in the Boolean expression in the next lecture.